Alright guys, in this video we are going to be looking a little bit more at the titrations math. So far we've gone over how to find basic pH and things like that. And with titrations we've also looked at how to find that equivalence point. We're going to be going a little bit more in depth, including what happens when you have a weak acid and a weak base that are added in there. So far, we've only talked about strong bases and strong acids. And we've talked about, starting off, that initial pH is going to be based off of the molarity of the acid. As you add base, the pH is going to start going up, but the pH will still be determined by how much excess hydronium you have because all the base that's been added has been neutralized. Whenever we reach that equivalence point, which for strong acids and strong bases should be at a pH of 7, that, remember, is where the moles of acid and moles of base are equal. Now, as we keep adding more base, we now have excess hydroxide. So that amount of hydroxide can be used to find pOH and pH. There's a summary of these titration curves in the middle of page 772 in our textbook. So whenever we're going to be titrating a strong acid with a strong base, anywhere before the equivalence point, the pH is determined by the amount of unneutralized strong acid. So you have to look at how much acid has actually been canceled out and then use the remaining amount to find pH. At the equivalence point, the pH will be equal to 7. And after the equivalence point, the pH will be determined by how much excess base we're going to have. So here's a sample problem that we may see with the strong acid and strong base. There's supposed to be an extra line in here, excuse me. So we have 25 milliliters of a 0.2 molar hydrochloric acid that's titrated with 0.2 molar sodium hydroxide. First question wants to know where's the equivalence point. This is where we would normally do stoichiometry, looking at our mole ratio and everything. Because both of these are going to be at a 1-to-1 ratio and they are the same molarity, the equivalence point should be at the same volume. So if the molarities are the same and it's a strong acid, strong base, you can make the assumption that it will be the same volume. So it will be at 25 milliliters of the base being added. If you went ahead and did stoichiometry for this and you started off with the liters of your known solution, changed into moles of your acid, changed into moles of your base using your mole ratio, and then plugged into molarity, you would get the exact same answer in this case. Other things it may ask you, what is our initial pH? These are things that we can all use to find a titration curve. So our initial pH is based off of our beginning acid. So remember, the pH is determined from the molarity of our acid, our molarity of our hydrogen. So our pH is equal to the negative log, of the 0.20 because that will be the concentration of our hydrogen. And that will give us initial pH of 0.70. So that's where our titration will actually start. That will be the beginning of our curve. Then it wants to know the pH after 15 milliliters of sodium hydroxide is added. So this is going to be before our equivalence point. But we need to figure out how much has been neutralized. So what we tend to do is look at moles of acid versus moles of base and figure out how much is left. You can actually also set this up as an ice table if needed. That way you can look at how many moles have actually canceled. So if we have 25 milliliters of 2 molar hydrochloric acid, remember the whole deal with acids and bases are that the moles of acid and base are actually canceling out. So to find moles for our hydrochloric, we do the molarity times the volume is liters, so 0.025. So that will give us 0.005 moles of acid. We're going to do that same thing with our base. Our base, we have 0.20 moles times the volume of our base we're adding, so the 15 milliliters. That is 0.003 moles of base. So whenever we subtract these, we're going to end up with 0.002 moles of acid that has not been neutralized. Now, we do need our molarity in order to find pH, but now our total volume has changed. So our total volume, because we had 25 milliliters of acid and 15 milliliters of base, our total volume is 40 milliliters. So our molarity is equal to 0.050 molar. And if we plug in that for pH, negative log of 0.050, we get that now our pH would be 1.30. So that would be our final answer for that section. So anytime we're going to be dealing with the pH after some acid and base are mixed, remember you always have to change into moles and then subtract, figure out if the moles have canceled out or not. The pH at the equivalence point, so remember equivalence point, moles of acid, moles of base are equal. So for the strong acid and strong base, equivalence point, the pH is equal to 7. And then look at the last part. Our pH after 40 milliliters of sodium hydroxide are added. This is above the 25, above the equivalence point, so we should have extra base here. We know how much acid we started with. We had 0.005 moles of acid. We need to do that same thing, but now with 40 milliliters of our base to figure out how many moles of our base we have. So the 0.20 moles or molar times the 40 milliliters. That is going to give us 0.008 moles of base. So whenever we subtract, we have a difference of 0.003 moles, but now this is moles of base. Divide by our total volume. So 40 milliliters and 25 milliliters is 65 milliliters. So our molarity is 0.046. Now we can plug this in, but remember this will plug in to POH because it is moles of base, not moles of acid. So negative log of 0.046 is going to be equal to 1.34, excuse me. And remember, pH and pOH add up to equal 14. Let me scroll down a little bit so you can see. So when we subtract that from 14, we get that our pH is going to be 12.66. So these are points that you could plot on a titration curve to give you the general shape of the curve. And yet again, all of this was for a strong acid and strong base. So now we have to talk about what happens whenever we have a weak acid instead of a strong acid. So here's a titration curve. So you see the red one is the strong acid that we just went through. But what happens whenever we have a weak acid? We're going to talk about some of these differences. You'll notice the initial pH is going to start off higher. You're going to have a gradual increase, and then it's kind of flatline until it goes to reach the equivalence point. Now, if you remember, the equivalence point is in the middle of this straight jump. It is going to be at a higher pH than whenever it's a strong acid and strong base. And then the tail end will be identical because that will be based off of only the hydroxide. So here's some of the differences that you'll notice that we mentioned. So the initial pH will be higher whenever you're starting with a weak acid compared to a strong acid. The pH of the weak acid will rise fast at the start, and then it will slow until reaching the equivalence point. So this is going to be a buffer solution before it reaches the equivalence point. And the pH at the equivalence point will be greater than 7 with a weak acid because you're still using a strong base. So the equivalence point will be higher. Here are kind of the steps we're going to go through for titrating a weak acid with a strong base, and then we're going to do a problem together. So initially you have a weak acid, so the pH is calculated with an ice table and the Ka value for the acid. Before the equivalence point, the added strong base is going to create some conjugate base of the original weak acid. So we're going to have to use stoichiometry to calculate the amount of weak acid and conjugate base present and plug it into our Henderson-Hasselbalch equation to calculate pH. At the equivalence point, all weak acid has been neutralized and only conjugate base remains in the solution. So the pH is determined using base hydrolysis reaction and the Kb value, because we will no longer have any of the acid. And after the equivalence point, the pH is determined by the amount of excess strong base, so the exact same as if we were doing a strong acid, strong base titration. Here is our sample problem, and we're only going to do the equivalence point on this slide, and then the other questions I've moved to other slides, so we can work through them together. So here we have 50 milliliters of a 0.25 molar acetic acid solution that is being titrated with 2 molar sodium hydroxide. I did, on my paper, write out the reaction. It's going to be the acetic acid and sodium hydroxide. I'm going to try to write this small. Will produce the sodium acetate and water. So this is going to be a 1-to-1 ratio, so we don't have to worry about any of that stuff. For the equivalence point and our titration, you can simply do a stoichiometry problem. So remember, stoichiometry, we are going to start with liters of our known solution, which is the acetic acid. So we're going to start with 0.05 liters of acid. Change to moles using molarity. So we have 1 liter of acid is going to be 0.25 moles of acid. Use our mole ratio. So there was 1 mole of acid and 1 mole of base. And you can actually, because we have molarity and we're looking for volume, add one more step, because the molarity of our base is 0.20 moles of base per liter of base. So we can actually go ahead and solve for liters or milliliters at this point in time. If we multiply and divide going across, we get our answer is 0.063 liters or 63 milliliters. So equivalence point is found the exact same no matter if it's a strong acid, strong base or a weak acid, strong base. So that did not change. Where we're going to be changing is where we are going to be finding some of our initial pH and things like that. So let's look at our next part, our initial pH. So we said that we need to use our Ka value to find this. So looking at our overall reaction just for the acid, because remember we're going to have excess acid, the acetic acid, whenever it is in water, will produce the, excuse me, there should be a 3 there, the acetate ion, which is our conjugate base, and the hydronium ion. Now our Ka value for the acetic acid is going to be equal to 1.8 times 10 to the negative fifth. And we actually need to look at how much or what the concentration of the hydrogen or hydronium ion would be in order to find pH. So we need to look at, if we started with 0.25 molar acetic acid, so this is going to be the beginning of an ice table. Let me change colors so you can see a little bit better. So we have 0.25 molar. Remember, water does not matter, and we started with none of our product ions. So we're going to have to decrease our concentration of acetic acid, increase acetate, and increase hydronium. So our equilibrium concentrations are initially, we're going to have 0.25 minus X, X, and X. So we can plug this into an overall equation. And I'm trying to give me a little bit more room to write. If you'll bear with me one moment. Just make that go down an extra line. Here we go. So then we can plug that in with Ka. So the 1.8 8 times 10 to the negative fifth is going to be equal to x squared whenever we combine our products over 0.25, and we can ignore the minus x because there is a difference in 3 decimal places. So if we solve for x, we get that x is equal to 0.0021, which is going to be our concentration of our hydronium. So once we have the concentration of hydronium, we can plug in for pH. So it's going to be negative log of 0.0021. So our initial pH will end up being 2.67. So just like we stated before, this should be at a higher higher pH initially than if we were dealing with a strong acid. All of the problems with weak acids and weak bases will have a lot of ice tables. So this is one thing to give yourself space to write, as you saw with my problems up above. All right, let's look at the next part. It wants to know the pH after 15.3 milliliters of base is added. So we need to look at how much is actually neutralized. So remember, when we are neutralizing, we need to look at moles of acid and base that have canceled out. Now, when we're adding sodium hydroxide, remember the part of the reaction that is actually neutralizing is the acid is combining with the hydroxide from sodium hydroxide, and it's producing, remember these are reversible reactions because they're weak, it will produce the C2H3O2 negative and water. So this is before the equivalence point, so we just want to look at how much excess of that acid we are going to have. And you are going to end up having some of your acid and some of the conjugate base in there, which means we can use our Henderson-Hasselbalch equation. So in terms of moles, remember to find moles, you have to do molarity times volume, which is equal to moles. So if we do that for our acid, molarity times the volume, the 0.25 times the 50 milliliters, we're going to get 0.0125 moles of the acetic acid. We need to do the same thing with our base. So 0.2 molar acid times 15.3 milliliters is equal to 0.00306 moles of our base. And remember, we had none of our conjugate base beginning. So we do have excess acid, so we are going to end up subtracting all of our base. It will end up neutralizing. But remember, that amount will add on our product side. I'm going to scroll down a little bit so you can see a little better. So at equilibrium, or once we've neutralized, we're going to have 0.00944 moles of acid. None of our hydroxide will be left. It is going to be neutralized. And now we're going to have 0.00306 moles of our conjugate base. So because we have our moles of acid and moles of conjugate base, we can plug into our Henderson-Hasselbalch equation. So remember Henderson-Hasselbalch, your pH is equal to the negative log of our Ka, which from the previous part we looked up was 1.8 times 10 to the negative fifth, plus the log of our base over acid. Excuse me, I'm miswriting something on my paper. So our base is the 0.00306 over our acid, the 0.00944. When we put that in the calculator, we are going to get a pH equal to 4.26 at that point in time. Looking at the next part of the question, we're going to be looking for the pH at the equivalence point. And we had said at the equivalence point, all of the weak acid is going to be neutralized and only conjugate base is going to remain. So then we're going to have to do a base hydrolysis reaction using the Kb to find the pH. At the equivalence point, this is going to require us to do two separate ice tables. One to neutralize the acid and base, and then one to do the base hydrolysis with our conjugate base. So we're going to look at the first part, where we're just doing the basic neutralization reaction. So remember we said with our acid and our base, I'm going to write our reaction. We have our acid combining with hydroxide. My screen just went blank. Hang on. Here we go. To produce our conjugate base and water. So remember, moles of acid and moles of base will be neutralized. So remember, we found moles of acid to be the 0.0125 moles of base. So this is at our equivalence point, the 63 milliliters we had found back in the first step. If you do the 0.20 times the 63 milliliters, this will also be 0.0125 moles. And we had none of our conjugate base initially. When these neutralize, remember we're going to subtract from our reactant side, add to our product side. We're going to have none of our parent acid or parent base, but we are going to have moles of our conjugate base. Here's where we have to do our second ice table and go through the base hydrolysis to figure out our concentration of our hydroxide that will be produced overall. Now, when we go through base hydrolysis, our conjugate base is reacting with water. So this is going to be the reverse reaction essentially, because remember this is a weak acid, so we can end up with some of the acid returning and some of the base. Now, because we are going to have to use KB, we said. Remember, we need molarity. So our first ice table was neutralizing moles. Our second ice table will be utilizing molarity. So that's something that's going to be slightly different between these factors. In terms of molarity, because our overall volume is the 50 milliliters of the acid and the 63 milliliters of our base at the equivalence point, our molarity is the 0.0125 moles over that total volume. So it will give us a molarity of 0.11 molar. Remember, water isn't included, and we have none of our parent acid or parent base initially at the equivalence point because it was all neutralized. Whenever this goes through hydrolysis, we'll end up subtracting some from our conjugate base, and that will end up adding and producing some of the products of that reverse reaction. So we're going to end up with 0.11 minus X, X, and X. And remember, we did say that we needed to use the KB value instead of Ka value. So from the previous problem, our Ka value was that 1.8 times 10 to the negative fifth. Remember that Ka times Kb is equal to Kw. So you can do the 1.0 times 10 to the negative 14th divided by 1.8 times 10 to the negative fifth, and we get that our Kb is equal to 5.6 times 10 to the negative 10th. That's going to be equal to the x squared over, and we can ignore the x, so we can do it over 0.11. Solve for x, and that is going to be equal to 7.8 times 10 to the negative 6th, and that is our molarity of our hydroxide. So we can plug that into POH, do negative log. Our POH will be equal to 5.11, which means our pH will be equal to, once we subtract from 14, it will be equal to 8.89. So that will be the pH at the equivalence point. And remember, because it was a weak acid and a strong base, it should be greater than 7. This is the longest step in the entire process. Then we can continue on to what happens after the equivalence point. So that last problem we had is looking at for the pH after 85 milliliters of base have been added. This is going to be very similar to the ice table we did before the equivalence point, looking at how much is neutralized. So our original neutralization reaction is the acetic acid plus the hydroxide from sodium hydroxide, producing water and the acetate ion. Remember, we started with 0.0125 moles of acid, because when we're neutralizing, we neutralize moles. If we do the 0.2 molar sodium hydroxide times 85 milliliters, that is 0.017 moles of our base, and we had none of our parent or our conjugate base. When we subtract, the smaller value is the one for the acid. That should be a plus sign. There we go. So we have none of our acid left, but we have 0.0045 moles of our base and 0.0125 moles of our conjugate base. So we are going to be using the amount of hydroxide we have in excess in order to calculate pOH. But remember, that needs to be in molarity, not moles. So we will have to do the number of moles, 0.0045, over the total volume, so the 50 milliliters plus the 85 milliliters. So that is 135 milliliters. So in liters. That gives us a molarity of 0.033 molar hydroxide. Our pOH will be equal to 1.48. So therefore our pH will be equal to 12.52. So we completed all of those same points for a titration curve, but using a weak acid and a strong base. So here's what that titration curve will look like. So we started at a higher initial pH of the weak acid. Before the equivalence point, there was that sharp increase and then that buffer region where the pH does not increase that much. Once we hit the equivalence point, you only have that weak conjugate base, and our pH is going to be greater than 7. And after the equivalence point, we had the hydroxide in excess. And yet again, an explanation of this graph is on page 778 in your textbook. One thing that we can find from these graphs is our half equivalence point. This a lot of times can be used to determine what acid we're using. So our half equivalence point is the volume of the titrant added, where half the volume of the equivalence point. So if the equivalence point is going to be at 26 milliliters, the half equivalence point would be where it is at 13 milliliters, so half of that volume. At our half equivalence point, the pH is going to be equal to the pKa of that weak acid. Because at the half equivalence point, the moles of conjugate base and moles of acid will be the same. So this last factor will end up being 0. So that leaves that the pH equals the pKa. So here's an example of how you can find that half equivalence point. Or this is an example showing how it actually works. So the volume of titrant added is going to be half the volume of the equivalence point, because moles of strong base added is half of the original acid. So we have equal number of moles of our parent acid and our conjugate base. So that last factor we said would be equal to 0. Therefore, pH is equal to pKa. So this we can actually also use to help find that point on a titration curve. And like I said, this could also be used to identify which weak acid is being titrated at that point in time. We can also do all of these calculations based off of if we have a base that's being titrated with an acid. So a base being titrated with a strong acid is going to be represented by the line in black. So yet again, it starts at a high pH. It's going to increase until it reaches that equivalence point, which for the black line will be at 7. And then you're going to have excess hydronium that's added. So this is simply kind of a mirror image, if you flip it vertically, of our titration of a strong acid with a strong base. We can also titrate a weak acid, or excuse me, a weak base with a strong acid. It will start at a lower pH, undergo that same buffer region. Since we're using a strong acid, the equivalence point will be lower than 7, and then end identically to if we had a strong base with that lower pH overall. So let's look at these overall steps, and these will be very similar to our steps for a weak acid and a strong base, but we will be using more of our Kb values versus Ka values. So equivalence point is found the exact same with stoichiometry. Our initial pH, we're going to use the Kb for the weak base and an ice table to figure out that concentration of hydroxide. Between the initial pH and the equivalence point, we are going to complete the reaction stoichiometry, so we can do another ice table if need be, look at how much was neutralized, and plug our values into our Henderson-Hasselbalch equation. Oh, excuse me. At the equivalence point, all of our base is going to be reacted, and we're only going to have conjugate acid. Then that conjugate acid will go through hydrolysis to give us our amount of our base and hydronium ions left. So yet again, this will require 2 ice tables, just like when we started with a weak acid. But in this final step, we'll be using the Ka value in that last ice table. After the equivalence point, we've added more strong acids. We'll have additional hydrogen ions. So we'll use that excess hydrogen to calculate pH. So overall, the same steps, but where we were previously using Ka, we will now be using Kb. Here's a sample, and we're going to do the equivalence point here together, and then all of the other parts are on subsequent slides, just like we did last time. So here we have 25 milliliters of a 0.7 molar ammonia that will be titrated with a 0.5 molar hydrochloric acid solution. First thing we want to figure out is where's that equivalence point. So we do need our overall reaction. So when we have ammonia and hydrochloric, excuse me, remember that will produce ammonium ions and chloride ions. So this is going to be a 1-to-1 ratio, so we need that mole ratio in our stoichiometry. For titrations, we started with our liters of our known solution, so liters of ammonia, so 0.025 liters, and I'm just going to put base for ammonia since I'm trying to write small. Change into moles using our molarity. So 1 liter of base is 0.70 moles of base. It was a 1-to-1 ratio, so 1 mole of base is going to react with 1 mole of acid. And then our molarity of our acid was 0.50 moles per liter. So our equivalence point should be at 0.035 liters of hydrochloric acid. So now let's go through the individual steps for the weak base. So we're going to look at the initial pH first. So initial pH, remember we did need to look at how much ionizes using the Kb value since we are now dealing with the base. So I'm going to write our overall reaction. So we have ammonia and the hydrogen from hydrochloric acid. Oh, excuse me. The ammonia in water. I was trying to neutralize already. Producing the hydronium. Oh, excuse me, ammonium. And hydroxide. So we had 0.70 molar ammonium. And that's ammonia. That's the only thing we had. We're going to have to subtract from our reactant side and add to our product side. So that will be 0.70 minus X, X, and X. So remember, since we have hydroxide, this is going to be using our Kb value. Our Kb value for ammonia is 1.76 times 10 to the negative fifth. It's still products of reactants, so it will be that X squared. And since the Kb and our concentration for ammonia are 3 spaces different, we can use the 0.70. X is going to be equal to 0.0035 molar, which is equal to our hydroxide. So when we plug into POH, it will be 2.45. Therefore, our pH will be equal to 11.55. So that's where our initial point is going to start on the titration curve. So still basic, but not the super high pH as if we were starting with a strong base. All right, let's find the pH after 10 milliliters of the acid is added. So we are neutralizing, so we need to actually write what's reacting together. So we have the ammonia is reacting with hydrochloric acid and water, produces hydronium ions. That will produce the ammonium ions and water. Now remember, when we're in the neutralization process, we need to be using moles instead of molarity. So moles of ammonia, if we do the 0.70 molar times the 25 milliliters, is going to be 0.0175 moles. For the acid, same thing, find moles. We have 0.50 molar times the 10 milliliters, which is going to be 0.005 moles. And we had none of our products. The acid is the smaller value, so that will completely neutralize. leaving us with 0.0125 moles of ammonia and 0.005 moles of ammonium. Once you have your base and the conjugate acid, you can plug into our Henderson-Hasselbalch equation. Now, remember, our Henderson-Hasselbalch equation had Ka, not Kb. So be aware of which number you're actually plugging in. So our pH is equal to the pKa plus log of base over acid. So we do need to change our Kb value into a Ka value. So do the 1.0 times 10 to the negative 14th divided by that 1.76 times 10 to the negative 5th. And we get that our Ka value is 5.7 times 10 to the negative 10th plus the log of base over acid. So our base is the ammonia, the 0.0125, over our acid, the 0.005, and our pH is going to be equal to 9.64. The common mistake here is that people try to plug in the Kb instead of the Ka value. If we plugged in Kb, we would have to rearrange our ratio of base over acid. Then it wants to know the pH at the equivalence point. This is the one that's the more difficult one, similar to when we started with a weak acid, because it does require two ice tables. One to figure out how much of the conjugate is produced once all of the acid and base are neutralized, and then one to go through hydrolysis to figure out what the pH would be from the reverse reaction. So our original reaction is the ammonia and the hydronium from the acid producing ammonium and water. So we said this is the one that is still with moles because we're neutralizing moles. So our amount of ammonia was the 0.0175. Moles of acid, whenever we're at the equivalence point at that 35 milliliters, will also be 0.0175. And we had none of our products. We're going to neutralize all of our acid and our base. Which leaves us only moles of our conjugate acid. That conjugate acid has to go through hydrolysis. So this was the reverse reaction. But remember, this second ice table needed to deal with molarities instead of moles. So the molarity for this, we're doing the moles of our conjugate acid, the 0.0175, over the total volume. So that's the 25 milliliters plus the 35 milliliters, which is 60 milliliters. So our molarity is going to be 0.29 molar ammonia. And since we had neutralized all of our original aster base, there's none here. So we're going to be subtracting from our reactant side, adding on our product side. So then we will end up with 0.29 minus x, x, and x. Now note that we are dealing with ammonium. So whenever we plug this in, because we have ammonium and H+, we will be using the Ka value. So the Ka value we had found in the previous problem to plug into Henderson-Hasselbalch, excuse me, let me scroll down so you can see, is 5.7 times 10 to the negative 10th. That's going to be equal to x squared over the 0.29, because we can ignore x. That's going to give us an x equal to 1.3 times 10 to the negative fifth, which is the molarity of our hydronium. So to find pH, we simply plug that into our pH equation. So negative log of 1.3 times 10 to the negative fifth will be a pH of 4.89 at that equivalence point. So remember, since we're titrating with a strong acid, the equivalence point pH will be lower than 7. The last process was after the equivalence point. After the equivalence point, we are going to have excess acid, but we need to figure out how much excess acid we have. So we do need to go through the same neutralization of the ammonia and hydronium from water, or excuse me, from the hydrochloric acid, producing the ammonium and water. Remember, we started with 0.0175 moles of our base. For moles of our acid, if we have 0.5 molar times the 48 milliliters, that will be 0.024 moles of our acid. When we neutralize, we're going to run out of base because our acid is the larger number. So we're going to end up with 0.0065 moles of hydronium. So that's what we can use to find pH. However, pH needs molarity, not moles. So we will have to do our moles over our total volume to find molarity. Our total volume, the 25 plus 48, will be 73 milliliters. So our molarity is 0.089 molar hydronium. And when we plug that in to pH as the negative log of 0.089, our ending pH here will be 1.05. So it was the same steps as with a weak acid, just going in the opposite direction. One thing we're not going to have to do math for are polyprotic acids, but I wanted to show you how these are different. Remember, each acid is going to come off at a different point in time. So you will end up with a graph with two equivalence points. One for the removal of that first hydrogen, one for the removal of the second hydrogen. But you do not have to worry about math with these.